staff of the College of Science at the University of Notre Dame, it is my great pleasure to give this gift of a Christmas lecture to the community. Please put your hands together for the one and only Dr. Michelle Thaller!
Oh, wow. I'm not sure I've ever had an introduction quite that good. Thank you so much, Kate. Oh, what an honor to be with you. Thank you for spending a little bit of your Christmas holiday time with me. And I'm just thrilled to be here. This is my first time in South Bend, first time to see the University of Notre Dame. And I'm so impressed with your community. I'm so happy to be here with you. So tonight we get a chance to take a little bit of a pause. Christmas is a time to me, of quietness, of contemplation, also family. You know, there's all of the parties, there's all of the presents, but there's something to me that's wonderful about the dark times of the year. You know, being an astronomer, I've always felt that the night sky was like an old friend. A lot of people tell me they feel this way. There's a group of people around the world that when you look up at the stars at night, you feel a presence. You feel as if you're somewhere sacred. And growing up in Waukesha, Wisconsin, I used to take night walks outside with my dad in the winter. And we would look up at the stars, and it really seemed like there was a connection between us and the stars. I felt that very, very clearly when I was a child. And that really sustained me through my career as an astronomer. So for me, astronomy is not about the study of things that are very far away, but it's the study of us, of where we come from, of what our origins are. And we're going to talk about that tonight. And we're going to talk about some beautiful new things that we've discovered with the latest large space telescope that was a Christmas present. It actually launched on Christmas morning 3 years ago. And I hosted that launch for NASA, and we'll see some of the images from that. But I want you to come with me tonight in the sense of something sacred, of something really beautiful. The images that I'm going to show you tonight, and we'll talk about what these are images from this new James Webb Space Telescope. And when we look at the sky, and when we look at things in space, we have to use different types of units, different types of ways of describing how big these objects are. This is a relatively recent image from the telescope, and we're going to go through exactly what this is in the talk. But every little dot that you see there, every little dot of light, is a star the size of the sun or even larger. The sun itself is a big object. People don't often realize you could fit 1 million Earths inside our star, the sun. That's how big it is. But yet, the distances that we're going to talk about tonight are larger still. And as astronomers, we can't really describe things in miles or kilometers. We all use the metric system. But we're going to use larger scales, otherwise we'd be writing zeros all night. And one of the things I'll talk about is a light year. Now, a light year is the distance that light travels in 1 year. Light travels in space at 186,000 miles per second. And so you let something travel at that speed for a year, and you cover about 6 trillion miles. So when I say a light year, that's the distance light travels in a year, about 6 trillion miles. This wonderful property that light takes time to travel is also something that means looking out into space must necessarily be an act of looking back in time. When you look at the sun, our nearest star, the sun is about 93 million miles away, and it takes light about 8 minutes to get to us from the sun. So we never see the sun as it is right now in the sky. We see it as it was 8 minutes ago. The nearest star to us, which is actually the brightest star in the southern hemisphere, Alpha Centauri. Alpha Centauri is about 4 light years away. So when we look at that star, we see it as it was 4 years ago. The reason we build bigger telescopes, and we want new telescopes that look at the universe in different ways, is that the more powerful the telescope is, the farther away we can see, the fainter objects we can look at. And so eventually we start looking at things in the night sky. The farthest thing you can see with the unaided human eye is the Andromeda Galaxy. It's just a little smudge, but you can see it on a very dark night. That's 2 million light years away. So when we look at that object in the sky, we're seeing it as it was before any sort of modern human society that we would recognize existed. One of the amazing things about the universe is that we know that it changed. This telescope that we'll talk about tonight has the power to look not only millions of light years away, but many billions of light years away. And we're seeing light coming to us that when it left the objects, the Earth itself hadn't formed, the sun hadn't formed. Amazingly, looking farther and farther back, we see the universe has changed substantially. The sort of chemistry that makes us up, we are made of things like carbon atoms, I'm breathing oxygen. All of those chemical elements become less and less prevalent as you look farther away and farther back in time, until eventually, and a friend of mine got the Nobel Prize for this in 2007, we can look back to a time with some of our instruments before there was anything except for the simplest chemical elements, hydrogen and helium. There's a story in here about life, about us, and about how we came to be and just how connected we are to the universe. So let's explore that a bit. This is an artist's conception of the James Webb Space Telescope in orbit. I'm just going to call that Webb from now on to avoid all of those syllables. Webb was something very audacious. We'd never built a telescope this scale. You see the mirror that is reflecting some distant galaxy light there is a segmented mirror, 18 segments. And this telescope is so big, we had to think of a very unconventional way of getting it up into space. So we're going to tell the story of exactly how we did this. The Hubble Space Telescope was launched more than 30 years ago. And that has revolutionized our view of the universe. But we knew that there was something else to be seen. And so about 25 years ago, we started working on this new James Webb Space Telescope. Now, I'm going to pause for a second to talk a bit about why this view of the universe is so different than anything we've seen before. The James Webb Space Telescope does not look at the universe in the same type of light that our eye does. And it took a while, it took until the 1800s actually, to discover that there were types of light that the human eye does not detect. There are types of light all around us in the room right now that actually you and I are all blind to. And they exist I mean, it's just like regular light. It happens to be energies that our eyes, our retinas, and our rods and cones don't register. So in fact, there is a whole variation of colors of light that scientists call the electromagnetic spectrum. That basically means every energy of light that exists. You see that there is this wonderful sort of rainbow here. These are the colors we're familiar with. And colors are how the human eye interprets different energies of light. The highest energy light that our eye registers is the violet or purple color, and the lower energy is the red color. So this is actually a whole spectrum of energy, just different colors we don't see. The highest energy light are things called gamma rays and X-rays and ultraviolet. And we're familiar with sunburns or X-rays where the light actually goes right through you. It's so high energy. Things that are slightly lower energy, that our eye just can't detect that low energy light, are called infrared, beyond red. That's the root of that word. And it's exactly the same, it's light. It's just a color our eyes are not sensitive to, and it's a lower energy light than our eyes register. And a lot of people are surprised to learn that microwaves and radio waves are actually forms of light as well. A radio wave is not a sound wave that goes through the air, it's a light wave that then we build instruments to detect and translate into sound. So radio is actually a light wave. And in order to demonstrate what the universe looks like in this different form of light, infrared light is all that Webb sees. Webb has no detector that is able to register the visible light that we see. It's all infrared. Not sure if I said that wrong. Infrared light is all that it sees. So the images that I'm going to show you tonight are not visible light images. Your eye would not be able to see them. This is an invisible universe, unless you had eyes that could see infrared. Infrared technology has been incredibly useful because you've probably all heard of night vision cameras, things that can pick up the heat of somebody, even if you can't see them in the dark. There's also wonderful properties that firemen use them to actually look through clouds of smoke to see where people might be trapped in a fire. And what I have here today is an infrared camera. So with my wonderful assistant here, this is a camera. When I first started working at NASA, I bought some of these cameras to use in public demonstrations, and a camera like this cost $50,000. That's when I started in about 1997 in NASA. I just retired after nearly 30 years. And now these cameras are only a couple $100s. And so I think what we can do actually is switch to the camera. And you can sort of see, I'll focus in on myself there. There we go, yes. So I have a pretty cold nose. What you're looking at here, if you notice this scale over here on this side of the screen, the colors here are mapping to the temperature in Fahrenheit. We had to change that because this is a United States lecture. And so the darker colors are where my face is about 68 degrees, and then the light colors are where I'm up in the 90s. The internal temperature is somewhere in the high 90s of a human body, but on the surface a little bit cooler. If you look at my nose, I'm sure you can feel when you breathe in and out, it feels cool when you breathe in and warm when you breathe out, and you can see that. My teeth are wet. They're in my mouth. If I draw breath in, they cool off. So you can see all of those things. So you're looking at different colors of infrared light. So the images that you see tonight, a lot of people talk about the word false color. And I really don't like that false color because it kind of means that we're making something up, which we're not. At NASA, we like to call it representational color. There's no way that you can see infrared with your eyes. This camera detects it. And so in order for us as human beings to enjoy this, we map colors onto the different colors of infrared that we can't see. So I believe I actually asked for some volunteers. Do we have some volunteers that are ready to come up? We have one? Is there anybody else? Two people? Thank you. Please come on up. Yes. Hi. It's nice to meet you. My name's Michelle. What's your name? Allie. Allie? And how old are you, Allie? 7.5. Thank you for helping me today. And what's your name?
Cora.
Cora. And how old are you, Cora?
9.
9. Okay, so we've got some great volunteers. 9.5. Very important. I understand. So if we could all look at the infrared camera. I apologize for turning our backs to you, but I want to make sure the kids can see themselves. Come over here so you can see yourself in the camera. You can look at the screen. Okay, there's Allie. You can see Allie's pretty warm, all right? We've got everybody going here. You've got a cold nose, and you're also wearing glasses, aren't you? Yeah, if you look over there at the camera, we can actually see you a little better. There you go. All right, now I've prepared some demonstrations so you can see exactly. Oh, look at how cold my hands are. Good Lord. Yeah, you guys have warm hands. I look like I'm a zombie or something. I mean, I must be dead. Yikes. So we have some things we want to look at in the infrared camera. Okay, one thing. We've got some warm water here. Do we have the ice cubes as well?
I don't know about ice cubes.
We have some ice cubes somewhere, right? Okay, someone's going to get the ice cubes. So the first thing I'd like you to do, and this camera person can help. I noticed you guys removed your shoes. Could you also remove your socks? It actually helps. Infrared is heat. Literally, you're looking at something that's warm and emitting that light. So if you kids start to kind of walk around, what you'll see are their footprints.
Cold?
Yeah, keep walking around a little bit. Yeah, that's right, you can back up. Yeah, you can do a little hopping there, yeah. Yeah, you could maybe like sort of draw something with your feet. You can sort of see, yeah, there you go, you can see that. So they're actually leaving their heat behind on the floor. And at least for a little while, for a couple of seconds, it works much better on a carpet that retains heat better. I have something here that is warm. And somebody actually heated up some warm water for me. And I think they actually made it a little bit too warm. I'm not going to put that in my hand. But you can see how warm that is. Now, being able to see something's temperature, something that, this is not glowing in visible light. But in infrared light, in a lower energy light, it glows. You can actually see that infrared. So in space, we can see objects that are not glowing like a star. The surface of the sun is about 10,000 degrees, and that naturally glows in visible light. But objects like planets, which are cooler, they actually, you can actually pick them up in the infrared. And here we have some ice. Okay, this is going to be fun. Okay, everybody take an ice cube. So just take an ice cube, and we're going to look at ourselves in the infrared camera. And let's put a little bit of this in here so I don't. being creative. Okay, so let's face the infrared camera. If you guys look in the camera and you can see, okay, for one thing, you can see what's happening already. Can you look in the camera over there? I know it's a little hard. And if you look at me, if you touch the ice to your face, I just had my makeup done. But if you hold it, you can also touch it to your clothes, by the way. You can write on your clothes if you'd like. If you want to write. So what they're doing is that they're just cooling things down. All they're doing with the ice cube, you want to get your faces even more wet? What happens if you draw all over your face with the ice? You can turn yourself kind of into a jack-o'-lantern with just glowing eyes. So, by the way, we don't have a chance on stage right now to have all the kids come up, but afterwards, one of the activities we have after the lecture is a number of infrared cameras that people can come and play with. So, okay, seeing something's temperature is really quite cool, but there's other things too. So let's see, how's this water doing? It's not too bad. Yeah, so if I hold my hand up to the water, you can sort of see that it's almost like lava. So now my hands are warming up. Very good. Yeah, I can see that. Yeah. Seeing something that's warm is one thing that we do with Webb. And as I said, for us, probably the most important application of that are seeing planets around other stars. Planets around other stars don't give off any visible light of their own. Planets are warm, but luckily not 10,000 degrees. They're not glowing like a star. And if you guys want to keep looking at yourself in the camera, that's fine. The person who has glasses, I actually want to sort of make a point of this. Could you hold this piece of plastic up to the camera? Yeah. So this particular piece of plexiglass is clear in visible light. Visible light goes right through it. But it blocks the infrared. And this is something that we call the greenhouse effect. There are things that let through visible light, like our atmosphere, but they completely block infrared. They keep the heat in. They're actually opaque to heat light. This is also why we need to build a space telescope to see infrared light. Our atmosphere does not let this particular type of light through. And so even though you can see her glasses are transparent in visible light, and she's got the plexiglass, in the infrared, it lets through none of the light. Okay, and the last thing I'll do, because there's a little element of danger to it, and I keep getting in trouble with the NASA lawyers for this, but the opposite is true as well. This is a regular black, hefty garbage bag. And the real magic of an infrared telescope is being able to see into areas of the universe that are hidden from us. So there are giant clouds of gas and dust in the universe, and we're going to take a look at those. And they block a lot of important things. Stars form inside these giant clouds. To understand how stars and planets form, that usually happens in a part of space that's hidden from us. I'll let you guys put your hands in, but first I'll just kind of start by putting myself in. So, the hefty bag is very transparent in infrared, even though it blocks visible light. And you guys have pretty warm hands. If you want to put your hands in there, and we can see your hands through that. Yeah, there you go. So, and you can even see her just like through the bag. You can sort of see her there. But the hands work really well. There you go. Your hands are getting a little cold with the ice there. There we go. Yeah. So these two wonderful people, and thank you so much. Let's give them a round of applause. Thank you for coming up. You guys can go back now. Thank you. And whenever it's convenient, we can go back to the slides. No problem. Infrared really does have particular advantages. And most of the universe emits its light in the infrared, in this lower energy heat form. Things that are as hot as a star are relatively rare. So NASA has built a number of telescopes to look at different parts of the spectrum. And by the way, these are not all of them. We have many, many more telescopes. But the Hubble Space Telescope was mainly visible light, saw a little bit into infrared. The James Webb Space Telescope sees entirely in infrared. And I started my career at NASA in the 90s on something called the Spitzer Space Telescope, which was one of our first big observatories, so the infrared. Okay. Obviously, the larger a telescope you have, the more light you can collect. The fainter objects you can see, the farther out into space you can see. And so for the Webb Telescope, we wanted to build it as big as we could possibly make it. And this was built at Goddard Space Flight Center. That's where I've worked worked since 2009. I went to become the assistant director of science there. And this particular instrument it's wonderful. It's being built here in a giant room that's actually thousands of times cleaner than an operating room in a hospital. And you see the people there in their all-inclusive suits to make sure that no stray hair or even little speck of skin, even a few cells, you don't want that to get on something that's going to be going 1,000,000 miles out in space where we can't repair it. It's made of 18 segmented mirrors. The entire diameter is about 20 feet. The mirrors are coated with gold because gold is very reflective for infrared light. It is, however, like electroplating. It's very, very thin coating. In the entire 20-foot diameter telescope, it's about the equivalent of 5 wedding rings worth of gold. So just very, very thin coating of gold. And in order to get this telescope to be very sensitive to heat from space, I mean, imagine trying to step outside and feel the heat coming from the stars. We had to actually cool the telescope down to very, very cold temperatures. We did that naturally. We wanted to launch it about 1,000,000 miles away, outside even where the moon is. The moon's about 250,000 miles away. And there, naturally, in the vacuum of space, it cools to below minus 400 degrees Fahrenheit. So we had to make things that would work at that temperature. This mirror was so large that we do not have a rocket at this point large enough to launch it in one piece. So the mirror had to be designed to fold up sort of like origami, and then unfold, of course, with no human interaction in space. And this is where a lot of hours of sleep were lost at my house, because when you launch something in space, you want to keep it as light as possible. Every little gram of mass means a heavier lift vehicle, something more expensive, or it means you need to take part of the telescope off, take an instrument off, because it was too massive. So there really weren't any backup systems. This had to work perfectly the first time, and we didn't have backup ways of unfolding it. Everything had to work perfectly. So there it is folded up. And I believe in the next video, yes, so I'm going to turn on this. This is actual footage from the launch of the James Webb Space Telescope. We're going to start in an elevator going up the largest rocket in the world today, the Ariane 5. And that's the equivalent of a little bit larger than a 10-story building. At the very top of the building, there is another clean tent. And you'll see people in clean suits again. And we're going to put the telescope right up on the nose cone of this giant rocket. It was launched from French Guiana. French Guiana is the European launch site. The Ariane 5 rocket is with a contribution that the European Space Agency made to this mission. It was launched in thunderstorms on Christmas morning, and we'd all been up the night before. So here's what happened that day.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
So you hear the announcer talk about a journey back to the beginning of the universe, and this telescope now has the power to see hundreds of millions of years farther back in time than we've seen with the Hubble Space Telescope. And that was one of the major goals of the telescope, also to see things like planets around other stars. But what followed after the launch was absolutely perfect. The rocket got us on exactly the right path out to the million miles away. What happened next was something that really I will remember for the rest of my life as one of the most stressful times. There were over 300 single-point failures. Different actuators had to release little bits. Pulleys had to pull. There is a giant heat shield that you see here in this illustration. You can see the large mirror up here, but then down below, there's a shield made of very, very thin, almost mylar-like material, 5 layers of it. That had to be pulled without tearing it. It had torn during testing. Of course, we worked on that. But there were 140 release mechanisms, as you can see, all the different deployment motors, and we were on a schedule. As the telescope went farther and farther away into space, it got colder and colder. And so deployment motors, they had a heating element, but the heating element was limited as to how cold that would work. So we couldn't take our time. We had to keep going, one thing after another, and if one single out of 300 commands didn't work, the whole mission was done. There were no backups. And there were times when we sent the command saying, okay, tell this particular pulley to pull, and we came back with a message it hadn't pulled. And then the question was, do we stop and wait? Or was it an error just in the message, not in the technology, not in the actual hardware? It turned out that, it was more an error in the signaling. So people were sending commands even though they weren't quite sure if the first one had deployed. That was quite something. In the end, every single part of it worked perfectly. So starting with some of the nearer things, the Webb Telescope not only looks at the very distant universe, it also looks at our own neighborhood in space, our solar system. This is a picture of Jupiter in regular visible light. This, I believe, I think this was a Voyager picture, a picture taken by the spacecraft that flew by Jupiter many decades ago. You see the famous big red spot, the storm, that at this time was about 3 times the size of the Earth. It's gotten a little bit smaller now. It's changing color. I mean, it's a giant swirling storm. It changes continuously. So here's what Jupiter looks like in the light that our eyes can see. And it looks astonishingly beautiful and different in the infrared light that the Webb Telescope sees. Remember that what we're looking at here, and this is kind of almost more of a grayscale, not a lot of color, we're looking at temperature. We're looking at readings of the temperature of the clouds here on Jupiter. And the red spot turns out to be warmer than the clouds around it. So in the infrared, it's brighter. It's giving more heat. At the poles, you see in the infrared the giant auroras, the northern and southern lights of Jupiter. These are auroras that would easily swallow our planet. Jupiter has a very strong magnetic field, and it makes spectacular northern and southern lights. And then something that a lot of people don't know about Jupiter, Jupiter does have a very faint ring. It's so faint that in visible light, if you were out at Jupiter, you wouldn't see it. But it's dusty, there are small dust particles, they're relatively dark, they're hard to see in visible light, but they're warmer than the surrounding space. Remember, the telescope is at minus 400 degrees. So anything warmer than that counts as warm. The telescope can see that. And there's one of the little minor moons of Jupiter that you see at the very edge of that ring. So the resolution is mind-blowing. The clarity of this picture. Remember, this was taken from basically Earth, only 1 million miles away from Earth. Jupiter is hundreds of millions of miles away. So, I mean, already we had this wonderful instrument. And then as an astronomer, my specialty is studying the life cycles of stars, how stars live and die. And this is a famous image from the Hubble Space Telescope in visible light. It was called the Pillars of Creation. And I think that's a beautiful way of describing this. This is a nursery for young stars. This is a cloud of dust and gas, mostly hydrogen, in space. It's fairly nearby. It's in our own part of the galaxy. It's on the order of about 1,000 light years away. And so what we see here is this wonderful collection of a huge cloud of dust. Every little dot that you see here is a star. And to give you an idea how big this is, okay, we said the nearest star to the Earth is 4 light years away. And just one pillar of this cloud, this is actually about 5 light years. So that's about, that's on the order of 30 trillion miles. And this is where you have stars forming. At the very tips of these pillars, we knew that there was star formation going on, but it's hidden inside that dust. So here, this gives you a little bit of a larger context. This is actually those pillars seen with a bit more of the area around them. If you're careful, you can see there are the 3 pillars right there. And the reason they're shaped like that is that there is another cluster of stars that have just lit up. And the stars, having just turned on, have heat and radiation and a stream of high-energy particles, protons and electrons, coming off them. And they are blowing away the cloud around them. They're making a big bubble in that giant cloud. So as big as we thought that those pillars are, there's a bigger cloud around them, giving birth to hundreds of stars. And because these pillars are forming stars at the tips are a bit denser. They're forming stars in there, and they can hold on against a wind of radiation and heat and particles coming from this new cluster of stars. So that's why they're shaped like that. And star formation in some ways is actually really quite simple. All you need is a lot of hydrogen gas and material in space, and eventually over time, part of the cloud will become a little denser than other parts. Just through, random gravity, another star passes by, and when one part becomes denser, gravity notices. And more material begins to move toward the denser part of the cloud just under the force of gravity. That's it. Nothing more simple than that. As you press all of this gas together, and you have 5 light years of gas to draw on, as all of that collapses and collapses into the center, eventually just the crushing pressure of gravity alone drives the temperature up to tens of millions of degrees. And this is the only place in the universe where nuclear fusion naturally happens. It's so hot that you ram particles of hydrogen, the simplest gas, together. You ram them so hard together they stick, and they form the next element, helium. The only place in the universe nuclear fusion naturally happens is in the heart of stars. Then you take the helium, you ram it together, and you form bigger atoms. You form oxygen, carbon, the things that make up our bodies, calcium in your teeth, gold. All of these things come inside the fusion centers of stars. The universe does not have another way to make an atom of oxygen that you're breathing right now. The only thing that makes bigger atoms is the hearts of stars. So what I'm going to show you now is we're going to go back to that Hubble Space Telescope picture. This is visible light, the type of light that your eye sees. Now let's see the way Webb sees the clouds. It's beautiful. All those stars were there. What happened, if you remember the black plastic bag, those stars were behind clouds of dust in this giant, vast cloud called the Eagle Nebula. And so all of that was shining, but it was shining in light that was being blocked in visible light, but the infrared, the heat light came right on through. Now, some of these stars, honestly, are just kind of photobombing. There are some of these that are not associated with the cloud. A lot of the stars back here are just farther away stars in our own galaxy. The cloud was blocking the light of all of the background. But then some of the stars nearer the cloud, I think this cluster of stars here, these are actually stars that are forming in the cloud, and we're going to take a real close look at what's going on up here, because it turns out we can look even more deeply into these areas where we believe stars are forming today. So this is a close-up, and it's a slightly different color of infrared, which is why we've chosen a little bit of a different color to represent it in. Infrared, just like visible light, has different energies, different colors of infrared. And so in a slightly different color, it really brings out the beauty of the cloud, light years of dust and gas. And at the very top, we see these warm areas, these warm little hidden dots, a big warm area here inside the cloud. And this is where we're going to go deeper and deeper in to try to actually see as close as we can to the moment of a star turning itself on. So here we are even closer up into one of those lumps on the cloud. And sure enough, in here are the regions where naturally the gravity of the cloud is crushing it together hot enough so that it will get hot enough to make a natural, sustainable nuclear reaction. And then we begin to build the building blocks of the universe. So with the James Webb Telescope, we've actually seen things that I never thought I would see as a physicist. I mean, we had an idea about how star formation worked. We actually drew diagrams. So this is an artist's idea that as all of this gas and dust begin to fall in toward the young star, they probably spin up and form a disk, just because things falling in under the force of gravity tend to spin up. It's the conservation of angular momentum. It's the same force that when you've probably seen an ice skater have their arms out, very sort of extended, and they're turning, and as they pull them in, they spin faster and faster. As gravity pulls in the gas, it naturally spins up, just according to the laws of physics. So we figured in there would be a disk, there'd be a young star somewhere hidden in this cloud, and we thought that there would be these giant jets of material coming out along the poles of the star, because the initial nuclear reactions of the star probably weren't stable. These are the birth pangs. This is a star trying to get the nuclear reactions going and jetting material out along the poles. So this is what we thought the formation of a star would be like. And this is a picture from the Webb Telescope that really blew me away, because it turns out it was pretty much what was going on. In this case, the young star is still hidden in a very, very dense part of the cloud. And there is a disk, presumably, a disk of material that is spinning around in here. But what we can see very clearly are these giant jets, in some cases light years across, that actually herald the birth of a star. And again, a time for Christmas, a time for birth, a time to see the miracle that is going on all around us. Looking deeper into some of these clouds, and again, these are now scenes that are happening inside the dust that we wouldn't be able to see, except for the infrared cameras. If you look over here, there are all of these little structures that are all jets from these young stars. So there's all these little, these I call them little, in reality they're trillions of miles across. But there are all of these little bursts of star formation over here. Here you can see a newborn star beginning to blow a bubble in the gas around it. This is wonderful. These weird kind of triangular shapes here are actually shadows. There's a disk in there, a young disk around the star, a disk of dust. And it's actually the star in the middle is casting shadows. The disk is blocking out the light on either side. And the wonderful thing about these shadows is that even over the lifetime of Webb, we've noticed that the shadows are moving, they're shifting. And we think that's because the disk inside there that's casting the shadow is beginning to form planets. We form out of that residual disk around a star. Gravity clumps it together into planets, and you can see the shadows. And over the years, they shift as we think planets are actually warping the shape of that disk as they form. This is the moment of birth of solar systems, of stars. Here's sort of a close-up of some of those. Again, every little jet that you see here, there's a new star with its jets, there's a new star with its jets. It turns out to be everywhere around us, and it is so beautiful. I think in scientific talks, a lot of time people kind of click through the images. I want you to have a chance to look at these. I find them beautiful, and I find them profound. So stars, like all of us, we have a life cycle. It may be hard to accept, but they are born, they only have a certain amount of nuclear fuel in their cores that they can use for these natural nuclear reactions, and eventually they burn through that material and they die. And stars can die in a number of different ways. Probably the one most important to us is when stars are a bit more massive than the sun. As they collapse and die, they set off a spectacular explosion. What happens really is that the core of the star turns off its nuclear reactions. They stop, just naturally. It's run out of fuel that it can use for its nuclear core. And all of a sudden, it was that nuclear explosion and all of the heat and all of the radiation that was supporting the star against the crush of gravity. The core of stars, we think, may turn off in a matter of seconds. It actually happens when you make the element iron. That's the element that makes our blood red. That's what we have in cameras and frying pans. That element, we think, the formation of that element in the core of a star is responsible for turning the star off. And in that moment where the nuclear reactions stop and there's nothing to support a huge gravitational mass like a star, all the layers of the star crush into the middle, and as they do, they set off shock waves. They crash into each other, and the star explodes violently in a supernova explosion. This is a supernova. This star exploded about 1,000 years ago. It's in the constellation Taurus. It's called the Crab Nebula. It resembled a crab to some astronomers a long time ago. 1,000 years ago, people did record the explosion of the star. It was visible as a bright new star in the sky. Some people wonder if the Star of Bethlehem, if the Christmas star, could have been something like a supernova, a star that appeared briefly bright and then faded away. We don't know. But in these swirls of gas, give you a sense, this particular cloud is about 10 light years across. A single star has blown its material up over the course of 10 light years, and it's still expanding outward at 2 million miles an hour today. It exploded 1,000 years ago, and it's still expanding outwards at millions of miles an hour. And the wonderful thing about these supernovas is that in them we find all of the building blocks of the chemistry of life. So here's another supernova remnant. This one is called Cassiopeia A, for those of you that like astronomy. And again, about the same scale, this bubble of material flying through space is about 10 light years across. And we were so surprised with the Webb Telescope to see how detailed and intricate all of the explosion was. What were these rings? How did these form? This is a shock wave of material flying out into space, heating up gas around it. And in some of these regions, we've been able to identify the specific elements that are forming there. We see here's where calcium is coming from. Here's phosphorus, sulfur, the building blocks of our chemistry and our life. And as I mentioned, the astounding thing is that this is not conjecture. The James Webb Telescope can see so far away, so far back in time. We can actually see about 13 billion years, a little bit more back in time with the Webb Telescope. That now we can see a time when the chemistry was very different. And that's why we start looking at the periodic table differently. For those of you that remember this from high school, those of you that haven't been in high school, just wait, you'll love it. These are all of the different types of chemicals that we're aware of today. And this is actually available from NASA, if anybody wants this. We now know what kind of star creates each different chemical element. So we've observed, I'm not going to go through this today. I would love to lecture on every single one of these. Dying high mass stars, the Big Bang only produced the simplest hydrogen and helium. Everything else was produced by dying stars, in some cases radioactive decay, and for some of these more exotic elements, they've only ever been made in laboratories that we know of. So, human-made merging stars, dying stars, but it's a new look at the periodic table, because now we've actually seen where all these elements are created in stars. Okay, to end, I want to go out to some larger scales and talk about what I find most beautiful about this. This is a picture from the Hubble Space Telescope, again, a visible light picture of a galaxy. And the word galaxy, I've always thought was an easy word to say. Galaxy, yes. We live in the Milky Way galaxy. A galaxy is a family of stars that travel through space together. They are gravitationally bound to a common center. All the stars orbit around the center of the galaxy. Right now, the sun is orbiting around the center of the Milky Way at about 500,000 miles an hour. And these stars moving through space together, the thing that I love about galaxies is how vast even a single galaxy is. So we talked about the sun being so big you could fit 1 million Earths inside it. So now at the scale of galaxies, let's talk about how the sun relates to a galaxy. If you have the sun at the scale where it's the size of the dot of an eye on a page of text, so you're reading a paperback book, look at the dot of an eye. The sun is that scale, 1 million Earths in there. How big would a galaxy be? And this is where my mind is the same as yours. I cannot perceive large numbers any better than any other human. So it becomes sort of a time of wonder. If the sun were the size of a dot of an eye, a galaxy like this would be a little bit larger than the Earth. So, imagine flying from New York to Los Angeles, somebody's reading a paperback book way down there. You've still got hours to go on your flight to get around the Earth. The scale even of a single galaxy is something profound. It's easy to say the word. These are wonders. Now, when the James Webb Space Telescope looks at galaxies, this is, again, is a Hubble, a visible light picture of a spiral galaxy. We live in a galaxy much like this. Our galaxy is so vast, of course, we've never sent a spaceship out to be able to look back. Our galaxy is about 100,000 light years across. And the farthest objects we've sent from Earth are the Voyager spacecraft. I think they're now about 20 billion miles away, so there's no way to see our own galaxy. But you're looking at these wonderful sort of cloudy, bright areas. That's a cloud of stars too numerous to see individually. And you see all of this wonderful dark dust that collects between the stars and in spiral galaxies forms a beautiful spiral shape. That dust, that dark material, is the thrown off supernova remnants, the corpses of dead stars. Stars that had ripped themselves apart and exploded over billions of years. And the gravity of the galaxy has gathered those into these beautiful big arms of dust. The dark material is the dust. It's where we come from. We literally come from this dust, made conscious. In the infrared, the dust is warm. So instead of seeing the stars, we see the scaffolding, the underlying structure of a galaxy, the dust that we're made of, the chemistry, the carbon, the silicon, the rocks, the gold, the silver, the molybdenum, everything that we know about. In this view, and I should have mentioned actually that this is the same galaxy in infrared and visible. In visible light, the center is blinded out by stars. You see the dark dust. In the infrared, it's interesting. The center is very cleared out. Those blue stars are very massive stars that are forming near a giant black hole. Every large galaxy that we have observed, there's a huge black hole in the middle. The Milky Way is comparatively small. It's only about 4 million times the mass of the sun. Some of the black holes that we are observing are as much as 10 billion times the mass of the sun in the middle of the galaxies. This is a slightly different look at the galaxy, and in this case, we've gone to a color of infrared where even the cooler dust that might be 400 degrees below zero, is allowed to shine and show us where it is. I mentioned that the sun and the Earth and everything around it is actually moving around the center of our galaxy at about 500,000 miles an hour. And the amazing thing is that as we do that, we pick up this material from space. We pick up, on average, about 100 tons a day. That's our estimate. And so falling out of the sky right now, and I mean that literally, coming at us in through space, it interacts with our atmosphere. There's actually layers in our atmosphere that contain different heavy elements that have fallen in from space. All of this stuff is coming down on us. And in these clouds, we've even identified things like the simplest molecules, organic molecules, that we're actually based out of. The amazing thing about being a human, and we're talking about Christmas and birth, and we're talking about the mysteries of life. We didn't just come, the material that makes up our bodies, we didn't just come from one star. There was not a single star 5 billion years ago that blew up, that created the cloud that then the sun and the Earth formed out of. We have been flying around the galaxy. We've been around 20 times in the life cycle of the Earth in the last 4.5 billion years. You have atoms in you right now that were picked up on the other side of the galaxy. When the dinosaurs existed, 60 million years ago, 100 million years ago, the sun and the solar system was physically on the other side of the galaxy than we are now. It takes us about 250 million years to go once around the galaxy. You have inside you billions of stars. The material in you right now, the iron in my blood, as I mentioned, we think iron is very important. We think it actually kills stars. The oxygen, the calcium. You're not just a star's dust made conscious. You are, each of you, a galaxy made conscious. You have the vastness of space and time inside you. You are a miracle. And, there are many religious traditions and ways to interpret it, but if you think about the dust made conscious, the dust made real, and to dust we return, eventually the sun as well will die, and all of our material will be scattered back into space. The cycle of this is so beautiful and so profound. And it means that every human being, and also every pebble and every blade of grass, but as humans, we are the ones perhaps made most aware of the universe around us. The universe will never see through your eyes again. You are unique. Your lifetime, your view of the universe, and everyone around us is a unique way of the universe to know itself, a galaxy made conscious. That's what every single one of us is. Every single one of us is a treasure. And I think at Christmas time, and when you think about gifts, and when you think about the people around you, in a time where there seems to be a lot of divisiveness, to step back and realize our common origins, every single one of us, a galaxy that opened its eyes. So, galaxies, however, it goes even deeper than that. And I just wanted to sort of show you, I won't talk about it much. With the Webb Telescope, we are now seeing farther out than we ever have. We've never seen these galaxies before. A single observation of an hour, we discovered dozens of galaxies that were so far away we've never seen them. Hour after hour after hour. We literally set the telescope on an observation, go out to lunch, come back and see a part of the universe we've never seen before. That's real. And this is a tiny bit of the sky. So this is a little bit of the sky. If you took a coin at arm's length, and you actually hold the quarter at arm's length as far away as you can and look at the eye of George Washington on the quarter, that's about the amount of sky that you see here through the James Webb Space Telescope. Every dot you see here is not a star, but an entire galaxy, a monster, a miracle of stars. So there you see that kind of looks like a galaxy, that looks like a galaxy. These are galaxies on edge here. But even these little dots, these tiny little dots are galaxies that are so distant that even to the Webb Telescope, they just look like pixels. But that is a galaxy out there, a galaxy we've never seen. We have a chance now with the Webb Telescope to have a ringside seat through the story of creation. How did we get here? How do stars get here? How do planets get here? What is our story? And you are made from the atoms and the molecules raining down right now from space. It is an incredible connection. So go all the way back to the little kid that liked looking up at the sky. As a scientist, the reward of that study is life-changing and has brought me so much joy and so much comfort through the difficult parts of my life. The last thing I want to say, in the introduction, they mentioned that I was inspired by Dr. Carl Sagan. I never got a chance to meet him. I was a graduate student when he died. He died in the 1990s, and his show had really inspired me. And this is all the way back in 1980. He was a wonderful communicator of science. And when the Webb Telescope launched, a lot of us are old enough that we were inspired by Carl Sagan. We asked the Sagan family if we could use his voice as a way to introduce the launch. And they don't usually do that, and they don't like to uncopyright his recordings. This is public use, so it's all fine. But the morning of the launch, they gave us permission. We had to wait until the morning of the launch. It was Christmas morning. It was the Christmas present from the Sagan family. And I want to end on what we think he would have said about the Webb Telescope. This is him speaking about another exploration in space, but I think it's very apropos. So let me begin the video.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
And we are worthy. And I'm so happy to be with you here in Christmas season, and thank you so much for letting me share this with you. Good night.